All right, our next set of notes talks about projectiles and circular motion. So what is a projectile? You think back to like when you were younger in class and you got in trouble in school because the teacher said you threw a projectile. Well, what in the world is a projectile? Well, that means you threw something through the room, or somebody else threw something across the room. Maybe it wasn't you. I'll say that it was you. Somebody got in trouble for throwing a projectile. Right? So, by definition, a projectile is anything thrown or shot through the air. Right? That's what a projectile is as a definition. So now let's go, if we took something and I throw something, like I throw this pen, what's the path of this pen if I throw it? Right? Does it go straight constantly? No, it doesn't go straight, does it? Does it go straight down? No. I'm going to throw it sideways and watch the path of the pen. Right? Did you notice it did this? Right? It made a curved path. Right? So if I were to draw that on the board behind me, my pen did this. It made a curved path. Right? It doesn't go straight. It doesn't go straight down. It goes both. It kind of goes in a blend of the two. So now let's think about throwing this object. What are the two forces that are acting on this? Well, one force I have going this direction, that's inertia. Inertia is saying that the object's just going to keep going straight, 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 straight if we were out in space. Excuse me, goodness, I'm burping like crazy right now, excuse me. So inertia says the object should go straight, right, if I throw it. But when we're standing here on the Earth, I've also got a force that's going this way, and that's gravity. And gravity is pulling down on that object. So if I take the pen and drop it, it's just going to fall because of gravity. Right? So we really got two forces acting on this thrown projectile. I've got inertia going straight out. I got gravity going down. And if I blend both of those, then what I do is I end up with this curved path. Right? Now, why isn't the path of this like this? Right? Because it's not. It doesn't go that way. It doesn't go this way unless I throw it that way. If I'm throwing it flat, it goes and makes a curve. Well, the idea behind that is that think about the pen, and what we talked about in the notes the other day is that when I let go of this pen, it begins to accelerate. It begins to speed up because of gravity pulling down on it. And that's the same idea as to why we end up with this curve, is that at first it's not falling very fast, and then it goes faster and faster and faster. So all of a sudden it starts pulling down more. So that's why we end up with this curved path and not just an angle. So this angle that I got here, this piece right here, that's not right. It doesn't make that. It makes a curved path. And that curved path, hint, hint, right, it's going to come back to haunt you, has to do it because of inertia, going straight forward, and gravity. And it's a blend of those two. And that was part letter B in your notes, is follows a curved path because the Earth's gravitational pull pulls downward, and the object's own inertia moves it forward. And then number 3, we blend these two to get a curved path. Now we go to throwing a ball. All right. Well, if you throw a ball, now on this one you can't take the ball and throw it up. All right. We're talking about actually throwing the ball straight, so that it goes straight out this direction. And I will tell you, it may sound really weird, but it's really hard to do, to throw a ball straight, because we invariably, our mind wants to make it go as far as we can. In order to do that, we throw it up in the air, so we make an arc and get it to go farther. Right? If you don't believe me, go outside and try that, and try and throw a ball straight out, and not throw it up in the air. Right? So throwing the ball, we consider that inertia going this direction, that velocity is a constant. Right? If you've ever been to like Cedar Point or the fairgrounds, where they have the thing where you throw a baseball and it measures how fast you throw the ball. Right? Well, we don't say that ball slows down before it hits the thing at the end of the game at the fairgrounds. All right? We say that when you let go of it, it keeps that same velocity all the way until it hits the back of the display. Right? So the constant horizontal velocity, that velocity stays the same the whole time. Then we got number 2 there. Says gravity causes vertical velocity, and that's an increasing velocity. So when that object falls straight down, it goes faster and faster and faster and faster and faster and faster. It's accelerating, it's going faster. So that one is not a constant velocity. It's changing. Only the inertia going this way is a constant velocity. All right? So number 4 on there says gravity becomes an unbalanced force and causes the ball to accelerate down. So we would consider gravity to be an unbalanced force causing the object to accelerate. Oh, you got to think back to the last chapter. We talked about balanced forces, which is the idea of a tug of war where nobody wins, and an unbalanced force where you have a tug of war and some team wins and it all goes in one direction. So gravity is considered to be an unbalanced force because we accelerate if we fall. Right? The inertia that's up there, that's a balanced force. It's always going that one direction. Right? So now, throw a ball versus a drop a ball. Ooh, this is one that's always hard. Every time I try and present this, so many people don't think that this is legit. Right? And that is, if you throw a ball straight, now you can't arc it, you can't go like this, right? It's got to go straight. If you throw a ball straight and you drop a ball at exactly the same time, they will hit the ground at exactly the same time, right? Which is really, really hard to imagine because it's like, ain't no way. It seems like the one that you throw is going to take longer. Nope. Because of this, we got these two forces, right? Gravity's pulling down, inertia's going forward. That inertia does not make the ball stay up in the air any longer. It just makes it so the ball ends up way out here, okay? But the ball still falls at exactly the same rate as if you just took the ball and dropped it. Now, another one that goes along with this that Mythbusters does, if you want, you can go on Mythbusters and you can watch it online, is they do a test where they do the idea of taking a gun and shooting a gun perfectly level and taking a bullet and dropping it. So that you go drop bang and you do them both at exactly the same time. Well, which one's going to hit the ground first? As long as we're talking about a perfectly level surface of ground. Neither one of them. They both hit the ground at exactly the same time. The one that you shoot is going to be way over there. The one that you drop is going to be right here. But they're both going to hit the ground same time. Right? And I know, again, it's really hard to imagine, but it's all because these two forces, they're separate of each other. Even though they blend and give us that curved path, they're still separate entities of each other. So under letter D, it says throw a ball versus drop a ball. And it says, number one, both balls will hit the ground at exactly the same time. They're just going to be really far apart. Right? And again, it's a hard one to visualize in your mind, but it does happen. Right? So, and remember, the reason for that is because acceleration due to gravity is 9.8 meters per second squared. No matter what, that forward inertia of the bullet getting shot or throwing the ball doesn't influence the speed at which gravity pulls down. It's still going to be 9.8 meters per second squared. All right, so that's the concept of projectiles, right? And throwing things. They always make that curved path. Now, the next thing we're going to talk about is moving in a circle. So, I got this thing here, I'm going to fling it around in a circle. Why does it go in a circle? Well, because there's a string on it, Mr. Pape. What do you think? And all right, well, yep, that's right. The string keeps it going in a circle. What if you cut the string, and what does this ball do? Well, it takes off. Well, you know what? We can actually determine where it's going to take off at, depending upon where I cut the string at. Right? What we call this thing is centripetal acceleration. It's an acceleration in a circle. Okay? So it's constantly accelerating. Well, that seems weird, because looking at it, it looks like it's going the same speed the whole time, doesn't it? It don't look like it's speeding up. But it is, because if you go back to the previous chapter, remember that an acceleration is a speed up, a slow down, or a change in direction. Now, isn't this thing changing direction constantly? Yeah, sure is. Always changing direction. So it's always changing direction. It's constantly accelerating the whole time, right? So it's, according to your notes there, it says centripetal acceleration is acceleration towards the center of a curved or circular path. So that ball is constantly accelerating, going towards the center. Why is it going towards the center? Because of the string. The string makes it go towards the center. It's exerting a force, a centripetal force upon it. Okay? So number two, remember that a turn is an acceleration because your speed changes. All right, so when I'm flinging that ball, okay, if the ball's going this direction, how fast is it going that direction? It's not going that direction. It's going this direction. All right? So it's got a speed this direction. It's got zero going that way. But then all of a sudden, if it turns, then all of a sudden it accelerates and speeds up going that direction. That's why a turn is considered to be an acceleration. All right, so number three, before you come into the curve, you're traveling at 0 miles an hour, or 0 meters per second to the side. And then number four, it says, but when you turn, you increase your speed to the side to say 15 meters per second. That's what I'm trying to describe to you. Is if I'm going straight at you right now, how fast am I going that way? I'm not going that way. I got a 0 meters per second going that way. But all of a sudden, if I turn this direction now I'm going some speed that direction really, really quick. Right? And what I'm describing there is saying, well, what if I all of a sudden turn at 15 meters per second? And I'm going to be going 15 meters per second really, really quick. So I accelerated because I turned. And it's not that I speed up going around the corner. I'm going the same speed, but because I changed direction, it's considered an acceleration. All right, well, what's centripetal force? All right, well, centripetal force, this is in quotations because it's not really a true force. All right, it's an imaginary force. What it is, it's a force holding the object in a circular or curved path towards the center of the circle. So this string is exerting a force on it, per se, keeping the ball going in a circular motion, right? Think of the idea of a playground ride that spins you in a circle, right? That per se, that ride is keeping you going in a circle, right? But it's not truly exerting a force on it, right? It's confusing, but know that string is keeping this ball going in a circular motion, right? Now, where would I have to let go of this ball if I wanted it to take off and go towards the computer, right? So am I going to let go of it when it's pointing here? Am I going to let go of it when it's pointing over here? Am I going to let go of it when it's pointing back here? Or am I going to let go when it's pointing over here, right? So where am I going to let go of the string to get it to come right at you at the computer, right? Is it going to be at A, B, C, or D? Well, let's see. All right, so let's see if I let go of it at A. So I'm going to let go of it right here. I'm going to go a little bit slower. So now A. It went that way. All right. So that didn't work. So if I want it to come towards you, then what I need to do, I need to let go over here. I need to let go at D. There's D, 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 D. Look at that. It came towards you that time. All right. So it actually goes at what would be considered to be tangent. Right? So if I have a circle, all right, and I'm throwing that ball in this direction, and if I want the ball to go this direction, right, then I want to let go right here so that it goes off at a 90-degree angle to where I am in the center. Right here is a 90-degree angle. Right? Ooh, there's some math for you on that whole idea of a 90-degree angle. All right, if I let go over here, it seems like it should go that direction, but nope, it's actually going to go this direction because that would be a 90-degree angle. All right, it's called tangent to that. That's what that term is. So, all right, well, I'm going to stop there for a moment. We're going to go on to video number 2 to talk about weightlessness. So.